In this lecture, we'll be talking about modeling social networks. So this is Module 6, returning to the motivating questions about Module 6. We ask, how can we detect events using social media? How does a social network evolve over time? And how can we model the spread of content in social media? So this lecture is primarily about this middle case, about how do social networks evolve over time. Specifically, we look at models of social networks and how we can create social networks randomly or generate them through some mathematical modeling. So to answer this question about how social networks evolve over time, we first ask, how can we model social networks, and what factors make social networks distinct from other kinds of networks? The main one here, or the main assumption that we make when we deal with social networks, is the small worlds assumption, which we'll talk about in a minute. So for the learning objectives for this lecture, we want to talk about or be able to define characteristics of the small world graph, generate random graphs, and describe methods for converting these random graphs to small world graphs. So first, what constitutes a small world? So early on in this class, we've already talked about the 6 degrees of Kevin Bacon, the idea of actor networks or networks composed of these sort of social engagements among movie stars have some relatively small set of paths or short paths to get from Kevin Bacon to any other actor in the movies. This idea of 6 degrees of separation, that between you and some random person in the world, there are only 6 steps, or five steps rather, between you and anybody in the world. In the terminology of graphs that we've been talking about, we can refer to this idea as short paths between arbitrary points, or that the diameter of small world graphs should be small. Also, if we take a given social network and we look at clusters of people or little groups of people composed of friends or people who have some kinds of relationships, like here, we make some assumption that most of a person's friends also know each other. So this is a homophily assumption, right? Where people who are friends with each other often have other friends who are also friends with each other. So there's this local sort of clustering behavior where lots of people in these clusters also know each other. So that's the intuition behind small world graphs, but we can get rigorous as we go through it in defining them. First, we say small world graphs should be sparse in terms of network density. They should have small diameter, like we said. There should be short paths between you and some arbitrary other node in the network. And they should have some high degree of clustering, that these groups of people who are all related to a particular node also should be related to each other. Now, we've talked about sparsity and being able to measure that with network density. We've talked about diameter and measuring that using shortest path lengths, but we really haven't talked about clustering and what does it mean to measure clustering. So we'll take a brief detour here and talk about this. So first, if I show you 2 different networks, I can ask you, which network is more clustered here. Now, both of these networks have the same number of nodes and approximately the same number of edges, but we have 2 very different structures. So what kind of measures of graph structure have we seen before that we might be able to use here? So we've talked about cliques before, where we can count the number of cliques of size k, and perhaps you could approach this problem this way and say, well, what's the largest k clique that we can find in both networks? And then do some comparison. But the issue here is there may be many cliques present in these graphs, and it's computationally intensive to try and find all of them. We talked about the clique problem is generally an NP complete problem. It's generally computationally hard. Another metric we've talked about that's already been mentioned in this lecture is network density, where we look at a particular network and we want to understand how many edges over all the possible edges exist in a particular graph. We have a metric for this for undirected graphs. We take 2 times the number of edges and we divide by the total number of possible edges, or n times n minus 1. Do the same thing for directed graphs, but we just drop that multiplicative factor at the beginning. And this lets us say, okay, given a network, we can say how many edges exist compared to how many edges could exist in this entire network. And we talked about how social networks generally have low density. That is, they are sparse. And this makes sense from a small world perspective, where most people don't know many, many random people in the world. They know some very small population of the world. But interestingly, if you look at both of these graphs, they're very different in structure, but they have approximately the same density. So that tells us that maybe density is not a really good metric for clustering. We've also talked about network centralization, where we can take a node and compare its centrality to all of the nodes in the graph to get some idea of how centralized or how important that node is in the graph. And this will work for any centrality metric that you want to calculate. So we can look at this top node, or this top network, and say this node in the middle has some high centralization, whereas most of the nodes in this bottom graph are generally uniformly centralized. And we have a way to extend this metric to centralization of the graph by comparing the node with the highest centrality in the graph and subtracting that from what could be the largest possible or the most central form of this graph. But that tells us something about the centralization metric, or the centrality metric that we want to use, and we have to do some normalization to do some comparison, which is not necessarily, which can be non-trivial at points, and really it doesn't tell us a huge amount of the structure of the graph if we want to understand the graph as a whole, though it does tell us some things about, is there a particular node that's very centralized. It doesn't tell us how, it doesn't capture this idea of clustering, or that most of your friends also know each other, that would be distributed throughout the graph. So we don't have that captured here. So this centralization metric is also not good for clustering. Now we have also talked about network modularity for doing community detection, or evaluating the quality of a given community assignment. The idea being that adjacent nodes with few edges should be in the same group. But again, if we go back to trying to understand which network is more clustered, modularity really only lets us evaluate quality of groupings. It doesn't really tell us so much about whether one graph is more clustered than the other, though you could potentially create some metric based on modularity here. So if we go back to this question about what network, or what metric allows us to evaluate these two different networks for the degree of clustering we find, what does it mean to have a good metric for clustering? What is if we want to describe this idea of like tightly clustered or high clustering, what should we need? Well, first we want to be able to have a metric that is scalable to the same or to arbitrary graphs, right? So we want to be able to compare the clustering of one graph to the clustering of a graph of a different structure, even if the graph sizes are different or the graph structures are different. So we need some normalization method here, or some way to at least compare closer to the idea that we have for density than for, say, network centralization, where by default you have some arbitrary number that you may then have to scale through normalization. So what does it mean to have a good metric for tightness in terms of measurement? So we talked about we need to have a measure that can be comparable across graphs of different structures, but we also need to have a metric that captures this idea of tight clustering. So what this means is if we pick a random node in a graph that we think is tight, like here in this top right graph, then we should expect that all the friends or neighbors of that node should also be connected to each other. This idea of the homophily aspect, that all of these people should know each other since they know you, which means that that group, that small subgraph around that random node, should be dense. It should know each other, all these nodes should be connected in some way. So that is, if a random person's friends generally know each other. This is the homophily assumption that we made. So to illustrate this, let's go back to the risk graph that we talked about several modules ago. It's a much more easily parsable view from a node, from a network perspective. And we want to ask the question, how do we measure this idea of local density? Well, we already have some idea for this. So recall from a couple of modules ago, we have this idea of egocentric networks, where if you take a given node, say Ukraine, and you say, well, what are all the neighbors of Ukraine? And that gives us the 1 degree egocentric network. And we ask, well, what are all the neighbors of Ukraine, and how are those neighbors themselves connected to each other? And that gives us the 1.5 degree ego network. So we see neighbors of Ukraine include Scandinavia, Northern Europe, Southern Europe, Middle East, Afghanistan, and the Ural Mountains. And we can do the same thing for any other node in the graph. Say Eastern Australia is connected to Western Australia and New Guinea, and those two nodes are connected to each other. So if we build this 1.5 degree egocentric network for Eastern Australia and Ukraine, then we see these structures here. And we want to evaluate some idea of how densely clustered these nodes are. So first off, we want to remove that target node. How did we build this 1.5 degree egocentric network? Because that just adds edges that don't really tell us anything. And now we have a subgraph that we can then evaluate density in. So here we can evaluate density in these two 1.5 degree ego nets. And on the left, we see a density of 1, and on the right, we see a density of a third. And we can use this density of these 1.5 degree ego nets, less the target node, as a local clustering coefficient. The idea is that as the friends of a random node are more tightly clustered or know each other more, that means we'll have more edges among these 1.5 degree nodes, and the density of this local network should be higher. We can use that as our local clustering coefficient. So if we look back at the RISC network, then we can say this cluster metric is the mean local clustering coefficient across every node in the graph, which is about 0.49, which tells us that the graph is maybe less clustered than it could be, but overall has sort of middling clustering. For the RISC board, we can actually calculate this local clustering coefficient average for every continent, and we get some interesting insights, like South America is highly clustered, Australia is highly clustered, whereas Europe and Asia are maybe less clustered than you might anticipate, given the large number of nodes. So if we go back to the two graphs that we were talking about, we can now evaluate how tightly clustered they are using the mean local clustering coefficient for every node in the graph. And we get these metrics here, that actually the graph on the left is slightly more clustered than the graph on the right. Now, there are alternative clustering coefficients. One is called the global clustering coefficient, also called transitivity, that works not by taking the mean over all nodes in the graph, but by actually calculating a particular metric for the entire graph in a way similar to what we did with network density. So the way the global clustering coefficient works is by looking at triplets of nodes and comparing them to triangles of nodes, that how many of the triplets in a graph are associated with a closed triangle. And we could just look at this ratio of triplets and triangles. Basically, we have the numerator as the number of closed triples, which is actually 3 times the number of triangles in a graph, and we divide through by the number of all triples in the graph. So how many of the triples in the graph are actually closed? So that tells us something about how tightly clustered this graph is. Because in the case where you have many of your friends who also know each other, you would expect to have a number of these triangles. In social networks and social network analysis more generally, you expect to have these sort of closed triangles more often than not, because if you have one person who knows 2 other people very well, then you would expect those 2 other people to also know each other. These open triangles instead are sometimes referred to as the forbidden triad, because they are, in theory, rare for social networks, at least for triples of people who have strong ties. So going back to the RISC map, we can ask, well, what is the global clustering coefficient here? Really is a question of the number of triangles versus the number of triples. So the number of triangles is pretty clearly 2 here, the triangle of New Guinea, Eastern Australia, and Western Australia, and the triangle of New Guinea, Indonesia, and Western Australia. But how many triples are there? So we count them. So there's 1 triple here, another triple there, so that's 2, 3, and 4. And we have 5, 6, 7, and 8. So that tells us there are 8 triples and 6 closed triples, or 3 times 2 triangles. And this gives us a global clustering coefficient of 0.75 for this particular subgraph. So then we can calculate the global clustering coefficient for this RISC network. And we see there's 36 triangles over 260 triples for a global clustering coefficient of about 0.42, whereas the mean local clustering coefficient is slightly higher, about 0.49. Now, the issue with the global clustering coefficient is it's often computationally much more intensive than it is to calculate the mean local clustering coefficient. It's very easy to distribute or parallelize the calculation for mean LCC, and doesn't take a whole lot of understanding beyond just, well, how many neighbors does a particular node have, and how many edges are in this 1.5 degree ego net, which you know which you can extract directly from the graph. Whereas calculating all of the triplets and identifying how many of them are closed can be a computationally intensive task. So oftentimes you see the mean LCC used, especially for larger graphs. So now that we've talked about the RI metric for doing clustering, we can return back to this idea of characterizing small world graphs. So for the first characteristic, we have sparsity. That is, small world graphs generally exhibit low density. We have small diameter. That is, the maximal shortest path between any two nodes in the graph should be relatively small. And then we have high clustering, or high mean LCC for the whole graph. We can ask some additional questions here when we talk about diameter or small diameter. How small are we talking? And we talk about clustering, well, really, how much clustering are we really talking about? Now, there are some rules of thumb here. Given a graph of n nodes, we can say a small diameter is generally diameter on log scale. So given n nodes, the largest, shortest path should be approximately logarithmic in n. For high clustering, this is less clear, but generally maybe it's some, it's not maybe as high as you expect, but maybe higher than 0.2. It's not very well defined what high clustering means, but we can talk about clustering in comparison to other kinds of graphs. But first, let's talk about how common these kinds of graphs are. So if we look at a number of different kinds of graphs, so the internet, mobile phone calls, email graphs, citation networks, the actor network like the Kevin Bacon network, and even E. coli and protein interactions, all of these kinds of networks exhibit small world tendencies. And in fact, many evolving networks exhibit these small world tendencies. So as I mentioned, small diameter, we have a good rule of thumb for that, about big O of log n, and high clustering is a little bit harder to do, or to nail down what a real value is here. So when we talk about small world graphs, we can say a small world graph is something, is a graph compared to something else. So when we talk about small worlds, what are we comparing to? So to answer that question, we need to understand, or at least identify, what kind of graph is not a small world graph. And there are a whole family of networks that we can talk about here in terms of random graphs. So what is a random graph? How might you randomly construct a graph? So say you have a graph, so we know generally consists of vertices and edges. Here we have two nodes, for example. We're going to assume that when we talk about random graphs, we're going to assume it's undirected just for simplicity. And we'll assume that we have some set of vertices. Maybe we know the number of vertices in our graph, the number of nodes in our graph that we want. And to create a random graph, we're going to go through all pairs of these vertices and randomly decide whether that pair exists or not to generate a random graph. So we take a pair of nodes, say v1 and v2, and then we randomly decide whether this edge exists based on some parameter, p, that we can say is the probability of a particular edge existing, and we can set it in the model. So what this model is called is the Erdos-Renyi graph, or the Erdos-Renyi random graph model, where you have some set of nodes and the probability of edges between pairs of nodes in this graph. Now we can ask, we've identified what the general construct is for these Erdos-Renyi graphs. Are these graphs small world? So to figure that out, we can check, do they have small diameter? And do they exhibit the high clustering that we want? So to evaluate the diameter for these random graphs, this ER model, we can ask a slightly different question. And rather than trying to calculate the expected degree, or rather the expected path length between two nodes in a graph, we can calculate a slightly different number and say, what's the expected number of pairs with no common neighbor? So that means that if you have two nodes, there's not some common neighbor between them, which means you have to have a path length of greater than 2. Because of the construct that we use, specifically we pin the probability of an edge existing to this parameter p, we can model this problem using the binomial distribution. And we can say for any pair of nodes, what's the likelihood, or what's the probability rather, of these two nodes not having a common neighbor. And it turns out we can calculate this as the binomial coefficient of n choose 2 times 1 minus p squared raised to the n minus 2 power. And critically, as n goes to infinity, this quantity 1 minus p squared will go to 0. because p squared is going to be some value less than 1, and 1 minus some value of less than or equal to 1 is going to be some value less than 1. So as we increase the exponent of this value, that value goes to 0, giving us that as n grows arbitrarily large, that the diameter of any ER graph has to be 2, because we would expect there to be no such pair for infinitely sized graphs that have no common neighbor. Well, these ER graphs must have small diameter, because the diameter is less than the log of the number of nodes, and is in fact very small. You can get from one node to any other node in the graph very quickly. So now we can go to the second characteristic of small world graphs, about whether ER graphs exhibit high clustering. So we say they do exhibit some feature of small diameter, but do they exhibit high clustering? So let's define clustering as the mean local clustering coefficient that we talked about before. So we'll go through every vertex in a graph G and calculate the density of that 1.5 degree ego network, subtracting out the target node V. So we can calculate this in expectation for these ER graphs. So first we ask, well, how many edges do we expect there to be in an ER graph? Well, we know the formula for density is 2 times the number of edges divided by n times n minus 1. So n times n minus 1 over 2 gives us this value, this quantity here. If we take the inverse of that, that actually tells us the maximum number of edges that we expect to see in an undirected graph, n times n minus 1 over 2. And then we can say, well, if we have n times n minus 1 over 2 edges, or possible edges, and our probability p of an edge existing, then we can say, well, in expectation, the number of edges that we expect to see in this graph is m. How do we want the ER model to behave if the ER model produces a graph with high clustering? So we want high local clustering, or the mean local clustering coefficient to be high. We want the overall density to be low. This is what we said is a characteristic of small world graphs. They have low density. So we now know that the expected number of edges in a graph, of an ER graph, is p times the total number of edges you could have based on the number of nodes you have. What we want to ask is, what's the density of this ER graph? So we can calculate this density through some slight change. Well, the number of edges E, we just calculated as being m, so we can get this density value here. We can rewrite that, because we know the value of m, and simplify that the density for an ER model is actually the same as our parameter p. So we directly control the density of these ER graphs by setting our parameter p, or the probability of an edge being created between 2 nodes. So for the expected local clustering coefficient for an ER graph, we now know the density of the full graph. What about the density of these 1.5 degree ego networks? So again, the local clustering coefficient that we want to be high here is the density of these 1.5 degree ego networks. But if you look at the density of any subgraph in the Erdos-Renyi model, it equals the same as the density of the full graph. We can go through the math for this, but for now we'll just say the local clustering coefficient for any one of these subgraphs in the ER model is p, is the same as the density for the full graph. And we can prove that. But this means that the mean local clustering coefficient for a given graph is the density of the graph. And since these two are the same, the only way we can get high clustering coefficients for ER graphs is by having dense graphs, which is the opposite of a small world graph. We want a small world graph to have high clustering coefficients, but low density. We want them to be sparse graphs. So Erdos-Renyi graphs, these random graph models, actually cannot be small world graphs. If the ER models are not small world networks, can we do better? So the ER models have a characteristic that we want, namely small diameter, but the only way we can get high clustering from them is by having high density. So can we create a new model that maintains this small diameter in ER, keeps high clustering, but reduces the density or keeps these sparse structures that we want? So in the late 90s, Duncan Watts and Strogatz introduced the Watts-Strogatz model to address this problem. So what they do, rather than randomly generating a graph from scratch, they start with what's called a regular graph, or a ring graph here. So you take some set of nodes and you connect them in a ring structure, and then you add additional connections to k over 2 neighbors. So here this graph represents a 4k regular graph, or a 4 regular graph, where every node is connected to 4 other nodes, and we keep this ring structure where each node is connected to its 2 immediately adjacent neighbors, and the 2 neighbors adjacent to that. Now this nicely maintains a high local clustering coefficient. That means if we take this middle node of these 5 nodes out of this structure, then the remaining 4 nodes are still nicely connected to each other. Unfortunately, because of this structure, we still have long average path lengths. This is the structure that we have for ER, the characteristic that Erdos-Renyi models have. We lose here because as you grow this ring structure, then the more nodes you add will directly increase diameter. Because as you add more nodes, because of the regular structure of this graph, you're going to add in additional hops. So to get from one side of the graph to the other side of the graph is going to have more and more hops to get to. So the insight that Watts-Strogatz had was, we take this existing graph, we structure it in the way that we've described, but then we randomly rewire edges with some probability parameter that we provide. So we take some random edge, we go through every edge in the graph, we take some random edge, and according to some probability parameter b, we then unwire it from wherever it was connected originally, and then wire it to a uniformly selected node from the rest of the graph. And it could be any node. It could be a node from very far away or another node that's very close. We just make sure that they are not self-loops. So you can imagine that as this b value approaches 1, then we're actually rewiring the entire graph into this random structure, and we get an ER graph. So this, as this beta value goes to its max value, then we have degenerated to the Erdos-Renyi model that we've already discussed. But it turns out for the regime between 0 and 1, as you increase this b slowly, so you can have relatively low values of beta, the diameter of this graph approaches that of the Erdos-Renyi model very quickly, meaning that you get the ability to go from one side of the graph to the other side of the graph very quickly with only a few or only a small number of rewired edges. So if we go back to the characteristics we want from a small world graph, then we can ask, does the Watts-Strogatz model have small diameter? Well, it does, because with this beta value, as we increase it slightly, we get closer to the Erdos-Renyi model, which we showed has very small diameter. So that's a check. And we maintain this high local clustering. But still, the Watts-Strogatz model is not a great model for small world networks. So why is that? And the answer lies in our characterization of the degree distribution, which is why long ago when I asked you to be able to create graphs from social media content, I asked you to also think about and be able to evaluate the degree distribution of those graphs. Because the Watts-Strogatz model gives us a degree distribution that looks like this. Here's an example for several different values of beta. And we can see this is primarily centered around degree 50. So this tells us something that the average degree here is probably about 50. But if we compare these Watts-Strogatz models to more realistic networks, we see real networks have long tails, that the likelihood or the probability that you'll encounter a very high degree k is non-zero. Whereas for the Watts-Strogatz model, the likelihood or the probability of encountering a very high degree node is essentially 0. So that tells us that the Watts-Strogatz model doesn't capture that aspect of small world networks, this long-tailed aspect of degree. And we can look at this in terms of degree distributions, saying that the Watts-Strogatz model has this general binomial structure where you have very few highly connected nodes, basically no highly connected nodes beyond some threshold, and most nodes have the same number of links. And we know in real-world cases that's not the behavior we see, where instead for real-world networks we see many nodes have only a few links, but we have some small but still not insignificant number of nodes that have very large numbers of links, these hubs that we've discussed before. So the Watt-Strogatz model gets us closer to this idea of small world networks. We have low diameter, we have high local clustering, we have low density. But now we want to make sure that we maintain this long-tailed structure where we can still have nodes that have high degree, where most of our nodes still have this low degree. So how do we do that? And the answer that we'll go through is called preferential attachment models. So to review the characteristics that we want low density, small diameter, high clustering, and this long-tailed degree distribution. So the major insight that we get for preferential attachment models is that networks are not static. In the Erdos-Renyi model and in the Watt-Strogatz model, we essentially create the network in maybe a few passes. So in the ER model, we have all the nodes in the graph that we care about, and then we look at all the pairs of the nodes and we evaluate whether we're going to create an edge based on our P parameter. For the Watt-Strogatz model, you could say maybe we do this in 2 passes where we create our deregular graph, and then we go through and do this rewiring. But critically, no new nodes are added to the network. Basically, all of the decisions about nodes and how nodes are rewired happen essentially simultaneously. Whether one node gets rewired to point to another node is completely independent of how rewiring worked for the previous node or the previous edge. So the preferential attachment model says, well, we know that that's not how real-world networks work. Instead, when a new node joins the network, it chooses how to connect based on some structure, underlying structure in that network, that what happens now is not independent of what happened in the previous moment. So this is an idea of dynamic graphs, so that you can slice up the graph into these time slices, where each node and how it gets added is a discrete event, and then we can evaluate what happens to the graph in that time slice based on previous time slices. So then we have to ask this question: when a new node gets added to the graph, it needs to get connected to the rest of the graph in some way. What kind of factors may drive how that node connects to the rest of the graph? So in a social network, online or offline, there are a number of things that you may expect. So there's popularity. A node comes in and tries to connect to the most popular node. So a new student goes to a school or a new school and wants to make friends with some popular kid. There's influencers, so early adopters or people who are paid by some brand name to try and push some new product, that when a new node comes into the network, this influencer may then reach out to them and try and influence them to do something. Maybe there's some financial incentive that nodes have to go where the money is, or connect in the cheapest possible way, so they have to somehow minimize the number of connections, so they want to connect to the largest node or the most influential node. Or maybe there's some dominance built into the network where you have some small set of people or small set of nodes who are dominant, and they are collecting most of the behavior, like Google getting most of the ad revenue, for example, or you have some celebrity, which may be some combination of all of these things. Ultimately, though, the key insight beyond the dynamic quality of graphs is this idea of the rich get richer, or also called preferential attachment. So that means when we have a given network at some particular time slice t, when a new node comes in and wants to join this network at t+1, it has to make some decision about who does v7 connect to? Who does this new node connect to in the graph? Preferential attachment models say the likelihood of connection is proportional to the degree. What this means specifically is the higher an existing node's degree, the more likely it is to receive an edge from a new node. So that's this preferential attachment idea, that the more a node gets connected, the more new nodes will prefer to connect to that node. And we can calculate this directly, so we know we know the degree of all the nodes in the graph at a given time t. So when a new node comes in, we can evaluate or select a node from the existing graph with likelihood based on its degree, by the degree of that node divided by the sum of all degree. And we know actually that the sum of all degree is actually 2 times the number of edges in the graph, since every edge in the graph contributes 2 degrees. So we can directly estimate what is, or rank rather, the nodes with the highest likelihood of getting a new link from this V7. So here in this graph, V1 has the highest degree by a pretty high margin. So the likely action that will happen here is V7 comes into the graph and then connects itself to V1. And it could connect itself to a few others. The number of connections made when a new node comes in is a parameter of the model. This is called the Barabasi-Albert model that you get to read about. And then over time, this V1 node emerges as a hub in the graph. There's some implementation details here about how do you initiate these preferential attachment models. The general way is to start off with some Erdos-Renyi graph, so you get some initial seed set of nodes, and then you can add new nodes to the graph until you get some target node count that you're looking for, and these hubs will emerge out of that structure in a way that's much closer to real-world kinds of networks. So the Barabasi-Albert model maintains this low density because we start off with an ER graph. It maintains a small diameter because, again, we start off with an ER graph and we have most of these nodes, most random nodes are coming in and connecting to these hub nodes or hubs with high degree, meaning that these hub nodes allow us to have quick and short paths from one node to other nodes. We have high clustering as these new nodes are clustered around these hub nodes, and we maintain this long tail degree distribution where sort of by design we build in the existence of these small number of nodes that have very high degree, whereas most new nodes when they come in will have low degree or whatever degree you've specified, and over time those low degree nodes are less likely to get new connections, so the hubs become richer and richer. So once a hub sort of established itself, it sort of collects new behavior, collects new links as new nodes get added to the graph. So now we can compare the degree distributions from the Erdos-Renyi and Watt-Strogatz models to what we get with the Barabasi-Albert model, and see that the Barabasi-Albert model does much better reflect this long-tail degree distribution. And in fact, based on this, we can then ask, what's the probability of getting a node of degree k? For the Watt-Strogatz or Erdos-Renyi model, as I mentioned, this is essentially a binomial model that we can evaluate. We can compare that to the function that generates the degree distribution for our Barabasi-Albert models. The likelihood of seeing some degree k, even if that degree k is very high, is still non-zero, but very low. That low degree is much more likely than high degree, but high degree is still possible. And we see this is called a power law distribution because we have k raised to some power. So then we can characterize what these network structures look like. With the binomial distribution, we can say, well, the average node will get the average degree. This average degree metric is a relatively good measure for a randomly selected node in this graph. Most nodes in the ER model or the Watt-Strogatz model will have a degree that's close to the average degree. Now, on the other hand, for these real-world models, these power law distributed models, the average degree is actually a really bad metric for the degree that you would expect to see when you take some randomly selected node. So the average degree was going to be somewhere in the middle of the degree distribution, but as we saw, most of the mass of the degree distribution is around low degree. So most nodes in this power law distribution, or most nodes in the Barabasi-Albert model, have very low degree, and you have only a handful of nodes that have really high degree, but the average is going to be somewhere between those because the high degree nodes skew the average away from most of the low degree nodes. We call these scale-free networks. These scale-free networks are characterized by the exponent in that k raised to some power, and we can show actually, and studies have been done on a number of different networks that showing that the internet follows this scale-free feature. Through evaluation from the structure of the internet, we've evaluated this gamma to be around 3.42. You can get some analytic solution to specify approximately what these coefficients are. Now, the scale-free model in these networks actually explains a number of phenomena that we see. So for instance, if I were to ask you, on average, how many friends do you have? You'd come up with some number. But then I might ask, well, how many friends does an average one of your friends have? So you have maybe 100 friends. What do you think the average number of friends each one of those 100 friends has? And if we actually run this experiment and do some calculation on this, we find that on average, each of your friends has more friends than you. This is called the friendship paradox. If I have 100 friends, then on average, maybe my friends may have 200 friends. And this actually holds in a number of different places, both online and offline. This is partially because of the structure of these scale-free networks, where the average is going to be skewed far away from where most of the nodes are because of these few hubs. So if we take some random node, that is u from the network, the likelihood of high degree is going to be low. That you're much more likely to select some random node with very low degree. But if you look at your friends and then their friends, you start to get 2 hops away, you're likely to encounter a hub, or at the very least, you're likely to have one of these hubs influence the overall average of the network, which pulls the average of your friends much higher than yours, than the number of nodes that you have or the number of friends that you have, yielding the friendship paradox. And we can see this as well here if we look at what's the maximum degree you may expect in some random network. So because a random network like an Erdos-Renyi model is relatively uniform, and we have these small paths or small diameter between arbitrarily selected pairs of nodes, then for random networks, you actually would expect that the maximum number or the maximum degree that you would observe is going to be logarithmic in n. Whereas for scale-free networks, you have a maximum degree that's going to be much higher. The likelihood of encountering the max degree may be relatively low, but it's possible, and there will definitely exist some of these high degree nodes, these hubs, in scale-free networks. So there's just much more space for these high degree nodes to exist. There's much wider variation, or the possibility for much higher variation between the small number of degree that most nodes have and what you could possibly have as the max. If you want to play around with these kinds of networks or the different kinds of graph generation models that we've described, so we've described Erdos-Renyi models, Watt-Strogatz graph, and the Barabasi-Albert graph, these are all ways to generate graphs or simulate graphs that have some real-world or not real-world characteristics. So Erdos-Renyi graphs are relatively not real-world in terms of the kinds of graphs we see in social networks. Watt-Strogatz models get closer, Barabasi-Albert models get even closer, and there are other more sophisticated and complex models as well. If you go look at the Network X documentation, you see a large number of these graph generators that let you sort of simulate graphs that you might expect to find. And the parameters for each one of these graph generators are parameters that we've already discussed. So the Erdos-Renyi graph generator has parameters for n, the number of nodes that you want to see, and p, the likelihood or the probability of edges between pairs of nodes. The Barabasi-Albert graph has the parameter n, how many nodes do you want to have in the graph, and the parameter m, how many connections does each new node have or create when it joins the graph. And there's others as well. So there's a power law cluster graph and extensions on the Barabasi-Albert graph as well. So you can go play with this and sort of construct your own kinds of graphs and compare the graph structures, the degree distributions that we've talked about, to some of the graphs that you've extracted from the social media analytics that you've done. Circling back to the learning objectives for this lecture, we've now defined the characteristics of small world graphs. Namely, they're sparse graphs with low density. They have low diameter, so small shortest paths between arbitrary pairs of nodes. They have high local clustering, and they have long tail degree distributions. We've talked about a number of different models for generating random graphs, so the Watt-Strogatz model and the Erdos-Renyi model. And then we've talked about methods for converting these random graphs closer and closer to small world graphs. And you can look at examples from Network X about how to use these models yourself in simulation. If you have any questions about this, reach out or post in the discussion forum. And that's it for this lecture on modeling the evolution of social networks.